My name is Ralph Cohen. I'm a faculty member in the Department of Mathematics here at Stanford, and I'm also the Senior Associate Dean for the Natural Sciences in the School of Humanities and Sciences here. Let me begin by saying what an honor it is for Stanford to host this event, the first Breakthrough Prize Mathematics Symposium. The symposium will begin with a panel discussion involving this year's, which is to say, the inaugural Breakthrough Prize winners, and it will be moderated by Yuri Milner. After lunch, has my microphone gone out? It's okay? Okay, good. After the symposium, there will be, after the panel discussion, there will be a lunch, and after lunch, the symposium will continue with the awardees each giving talks about different areas of mathematics with a particular eye toward what the future might bring. Now I'd like to begin by introducing you to the panelists, the 2014 Mathematics Breakthrough Prize winners. So I will do this alphabetically, and if you would, please come up. Sir Simon Donaldson. Simon is one of the world's leading geometers. He is a permanent member of the Simon Center for Geometry and Physics at Stony Brook University. Prior to that, he held professorships at Oxford University, and in fact, he was here for a year, and somehow we managed to let him go. And then he went and was a professor for the last 15 or so years at Imperial College London before going to the Simon Center. Donaldson did his PhD at Oxford under Nigel Hitchin and Sir Michael Atiyah, who was one of the 20th century's most influential mathematicians. His thesis revolutionized the study of four-dimensional geometry and topology by introducing new ideas based on Yang-Mills theory coming from physics. His new four-dimensional invariants became quickly known as Donaldson polynomials or Donaldson invariants, and their offshoots and their descendants became the most important technique in four-dimensional geometry and topology in the last 30 years. His innovative methods and results have had a huge impact across many fields of geometry, including differential geometry, algebraic geometry, symplectic geometry, and geometric analysis. Prior to the Breakthrough Prize, he won many other honors, including the Fields Medal, the Crawford Prize, the Shaw Prize. He is a Fellow of the Royal Society, and a couple of years ago, he was knighted for his services to mathematics. Maxim Kontsevich is a world... Go ahead, I won't stop you. Maxim Kontsevich is a world leader both in geometry and in theoretical physics. And the interplay between geometry and physics is a hallmark of his work. Indeed, he has the unique distinction of winning a Breakthrough Prize in Physics 2 years ago and now one in mathematics. He is a professor at the IHES in France, and he got his PhD at the University of Bonn in 1992 under the direction of Don Zagier. Kontsevich's thesis gave a proof of a conjecture of Ed Witten, another Physics Breakthrough Prize Award winner. Witten's conjecture was a conjecture in geometry motivated by a conjectural equivalence between two different models of two-dimensional quantum gravity coming from string theory. And Kontsevich's solutions to the geometric question established that equivalence in physics. He also introduced the mathematical notion of homological mirror symmetry, again inspired by ideas in physics, which has affected many areas of geometry and topology over the last 20 or so years. And he has done deep work in knot theory, symplectic topology, and algebraic geometry. He also introduced the notion of deformation, quantization. Among his earlier prizes are the Fields Medal, the Henri Poincaré Prize, the Crawford Prize, and the Shaw Prize. Jacob Lurie. Jacob is best known for his work in algebraic topology and its relationship to algebraic geometry. He got his PhD at MIT in 2004 under the direction of Mike Hopkins. He soon after that became a faculty member there at MIT, and he later moved down the road to Harvard, where he is now a professor of mathematics. In Lurie's PhD thesis, he introduced a subject that he called derived algebraic geometry, which applies techniques from topology, namely homotopy theory, into the world of algebraic geometry. He's also reversed the arrow, using algebrogeometric techniques in topology, such as his work on elliptic cohomology, an idea that grew out of Witten's work in string theory, and on topological modular forms, a topological realization of an important concept in number theory. Lurie developed the notion of infinity categories, which he has used to make breakthroughs in the classification of topological quantum field theories, as well as in number theory, the latter in joint work with his colleague Dennis Gates-Geary at Harvard. In addition to the Breakthrough Prize this year, Jacob became a MacArthur Fellow. Terence Tao. Terence began his career working on problems in analysis, in harmonic analysis and partial differential equations, earning his PhD at Princeton in 1996 under Elias Stein. Tao subsequently made tremendous contributions across many fields, such as combinatorics, ergodic theory, number theory, statistics, and he has spent his entire professional career at UCLA. He is known as a problem solver extraordinaire, and his breadth of research has completely obliterated the line between pure and applied mathematics. For example, his work with Stanford's own Emmanuel Candace on compressed sensing has had important applications in a variety of areas, and in particular medical imaging. In addition to the Breakthrough Prize, Tao has received many other awards, including the Fields Medal, the Alan T. Waterman Award from the National Science Foundation, the King Faisal International Prize, and earlier this year he was awarded the Royal Medal from the Royal Society. Richard Taylor. Taylor is one of the most influential number theorists in the world, playing a key role in many dramatic advances in the Langlands program in recent decades. He received his PhD in 1988 at Princeton under the guidance of Andrew Wiles, and held faculty positions at Cambridge, Oxford, and Harvard before joining the faculty at the Institute for Advanced Study in Princeton a couple of years ago. He became world famous beyond the number theory community in 1994 when his work with Andrew Wiles completed the proof of Fermat's last theorem, one of the greatest 20th century achievements in mathematics. By building on that circle of ideas and introducing many new techniques, Taylor and his collaborators have solved an amazing array of fundamental conjectures at the interface of number theory and representation theory, including the local Langlands correspondence for general linear groups and the Sato-Tate conjecture. Among his honors prior to the Breakthrough Prize are the Cole Prize from the American Mathematical Society, the Shaw Prize, a Clay Research Award, and he's also a Fellow of the Royal Society. Last, but certainly not least, I want to introduce our moderator, Yuri Milner. Yuri is a famous entrepreneur, investor, and philanthropist. The Breakthrough Prizes were his brainchild, and he, together with Mark Zuckerberg, sponsored the Breakthrough Prize in Mathematics. As I understand it, one of his goals in setting up these prizes is to make the world take notice and to increase the influence of the world's leading mathematicians and scientists. So without further ado, I introduce to you Yuri Milner and the 2014 Mathematics Breakthrough Prize winners.
Well, thank you very much for the introduction. And also, I want to thank Stanford, UC-Berkeley, UCSF for hosting today's events and for their hard work and care. Galileo said the great book of nature can be read only by those who know the language in which it's written, and the language is mathematics. Please forgive me if I'm not completely fluent in this language right now. But 30 years ago, when I was doing theoretical physics, I could get by with partial differential equations and Calabi-Yau manifolds. But if there is one thing that ruins your math skills, is the career in finance. So we have today 5 of the world's outstanding mathematicians, and the inaugural winners of the Breakthrough Prize in Mathematics, they will also form the committee to select future winners in subsequent years. So I wanted really, just given everything that I just said, I wanted to have a little bit of a philosophical discussion, at least that's the one I can maintain. And I wanted to ask the first question to all of you, which is the following. Is the mathematical world invented or discovered? And I can rephrase it by saying, if we were visited by aliens, would you expect their mathematics to be similar to ours? So you want to go first?
No. Well, certainly when I do mathematics, I have the very strong sense that I'm discovering something, not inventing it. Certainly in my field, we suspect what's true long before we are able to prove it through heuristic or experimental endeavors. And I have the strong sense there's something out there, I've just got to find my path through it. I think it's very likely that how could an alien civilization not have the same mathematics? They need to count. Counting is a basic operation. It can't be any different anywhere in the universe. Measuring is a basic operation. Anywhere in the universe, you'd have to measure time, measure space. So I strongly suspect that mathematics might be one of the few common languages we have, if there are civilizations elsewhere in the universe.
One of the few, or the only one?
So
the only one?
Maybe physics would be the same. Physical laws seem to be the same everywhere. Biology could well be different. You could imagine that it would be entirely different somewhere else in the universe.
Terence?
Well, I think mathematical theories, at least on the surface, they are invented. They're human constructs. But as we drill down and we discover deep facts, deep phenomena, as Richard said, there's a sense that they're not coming just from our formalism, but they're really reflecting something real. And as we drill deeper, often our language improves to approximate this reality. So we don't, maybe initially it's invented, but eventually I think we are doing discovery. That would be fantastic if we could ever contact an alien civilization and compare our textbooks. This would be wonderful.
No, there are more habitable planets, is it not?
Yes. Maybe in our lifetime. Even in our history, like Pythagoras' theorem was discovered independently by the Chinese, the Babylonians, and the Greeks. So there are mathematical facts that were independently discovered. Although the Greeks were the ones who actually tried to prove it. So maybe there are some things which maybe we can do better than the aliens. We don't know. Yeah.
We don't know. Maybe the other civilizations proved it, and we just have no record.
So I would agree on the first question that I feel as a mathematician like mathematics is something that is out there to be discovered. On the second question, I think I would disagree a little bit. I think some of the things that mathematics chooses to focus on are highly dependent on the way that the human mind works. So for example, the continuum of real numbers, that's something which is of major interest in mathematics, and it's very natural from a mathematical point of view, but probably a lot of our interest in it comes from the fact that it matches with our experience of space and motion and so forth. And especially in the subjects of geometry and topology, I think to some extent the successes that we've had in thinking about these things come from our geometric intuition. And that geometric intuition comes from our mental faculties for navigating the world repurposed to understand abstract mathematics. And if somehow we had much stronger mental faculties like that or much weaker mental faculties like that, then I could imagine our mathematics would look different.
Because I heard it theorized that the ancient Greeks, they were good at geometry because they needed it to navigate the mountains. and just to the terrain. And simply the British were good at spherical trigonometry for similar reasons. Anyway.
Yeah, and about this inventor to discover, I have not so rosy view of mathematics. Of course, really good mathematics is discovered, but a lot of most mathematics is invented should be forgotten. Yeah, and and about aliens, I think I agree with Jacob says it's really heavily depends on our physiology, and if it would be a completely different life form, then it could be maybe different aspects which we are missing here.
I agree with what Richard said. I think at least psychologically we feel that we discover things in mathematics, but there certainly is an element of invention. I mean, for example, when the introduction of the concept of zero, for example, would be something where you could maybe say that was an invention, or you take things which are more, to some extent, organizing. Ways of organizing knowledge, like, for example, the ideas of concept of a sheaf or something, which was introduced, and then you could prove things that could be proved before, but in a much shorter and more efficient way. So I think there certainly is an element of invention. As Jacob says, I think we can at least imagine that there will be parts of the universe where physically it will be quite different, where maybe space is discrete, and so there's no notion of measurement and geometry in the sense that we have. But I think, anything more digital, so based upon whole numbers, we could say that must be universal. So.
Well, I'm sure some physicists will disagree with your point that discrete parts of the universe are possible. But on that subject, Eugene Wigner famously said that there's this unreasonable effectiveness of mathematics in describing the universe. So, Richard, why do you think that the universe is described by mathematical laws?
I have no idea, but Terry, when we were discussing this earlier, had a very good answer, so I defer to Terry.
Well, we've been discussing this.
Yeah. Well, one possible mathematical explanation for why the universe, I think, so Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. And, a priori, there could be laws of nature at the molecular level, which, when you see them macroscopically, it would just be so complicated that you would not see any of the patterns that you saw at small scales coming up macroscopically. But in mathematics, there is this great phenomenon of universality, that if you have a complex system, many times it doesn't even matter almost what the individual particles are doing in a system. The macroscopic limit will be a universal law, which is almost independent. Like laws of thermodynamics are basically the same for both classical and quantum states of matter, for instance. And so that is perhaps a mathematical explanation. So even before we don't have a full understanding of physics at below the atomic scale yet. I mean, we're getting closer, but it's still not complete. But still, we can understand macroscopic things like continuous media, and so forth. And I think universality as a mathematical phenomenon is one of the explanations of that.
Maxim, you got the prize in physics, so you have to know the answer here.
Yeah, to this question, yeah, I really don't know. Yeah, because no. What Terry explained, it's only kind of mathematics applicable to large-scale physics. But why it's quantum mechanics, I found completely incredible. I think it's a good sign that we are just computer simulation or some mathematical constructs at the end of the day. So the quantum mechanics, it's a really impossible object, and I have very strong philosophical explanation for this, because I believe in vector spaces. Vector space is something strictly additive, and it's impossible because it's invention of mathematicians. vector additivity, when it's kind of limiting object process. When you have tangent space, you live infinitely long time to measure probability and so on. So I cannot really believe that nature can really vector space. It should be manifold. Yeah, so it's something completely incredible. Yeah, I'm baffled. Yeah.
So you do you really believe that we can be living in a simulation?
Yeah, I think we are actually not real. Yeah.
Well, this is definitely one of the explanations of the Fermi paradox,
Yeah.
if that's the case. But do you think there is any way to prove that we are or are not living in a simulation? Or you think we'll never be able to do that?
In fact, I read it, maybe crazy. For example, people measure this as, if you consider frequency of signals, this kind of very sharp bound, which may be the size of digital approximation.
Yes, I had this conversation, incidentally, a couple of weeks ago with Elon Musk, and he said that when is the time to switch off the simulation? And his theory was that when the people who are simulated will discover that they're simulated, then this is really this would be a good time to terminate. So.
Yeah, and in fact, also I've read some science fiction where eventually it was clear that science fiction, every civilization will realize it's a simulation, but it's okay. So it will be a common religion about all civilization. And okay, let's stop it. Yeah, this is nonsense. Yeah.
Okay, so I think I should be asking the next question here. And the next one is really about the unity of math. So Isaac Newton wrote, truth is ever to be found in simplicity and not in the multiplicity and confusion of things. So my question is, are the different fields of mathematics hiding a simpler system that we cannot see yet? In other words, like physicists are always seeking unification, is there any way that mathematics can be unified in a way that there will be nothing else to discover?
I don't think there's going to be one theory of all of mathematics. Mathematics concerns such different things. It concerns the whole numbers, which is essentially a discrete phenomenon. It concerns manifolds, which are essentially continuously varying objects. But what is very surprising is the number of times an idea in one area of mathematics suddenly resonates in another. So although I don't think we're going to have one law for all of mathematics, the knowing about lots of areas of mathematics is very helpful as a mathematician because you get these surprising interactions between the different areas.
Well, the slightly contradicts what physicists think, that because they are really truly looking for the theory of everything all the time, and you are saying that this mathematical discovery quest will never end.
Yeah, I can't imagine mathematics coming to an end somehow. Every time you discover something new, it raises new questions. So I don't see it as a finite activity.
I think you have to distinguish between the foundations of a science, where you want to work out the fundamental rules of the game, and then the theoretical applications of those rules. And I think mathematics is much further along in the foundational aspect. By the time of Hilbert, we had already worked out a common set of axioms that would suffice for pretty much all the mathematics. And in physics, we're getting close to that. I mean, the theory of everything is meant to be, I think, the analog of the mathematical of our modern foundations of mathematics, which are now pretty much uncontested. But that hasn't stopped mathematics. It's the applications on top of the foundations, which is still expanding and will never end. So the physicists, I think, even if they do find a final theory of everything, then they will have to apply it, each one of to solids, to plasmas, whatever, and that will keep going for a long time.
But I was talking about a set of interconnected areas and nothing is more fundamental than the other, or something is more fundamental?
Well, it's probably we shouldn't prejudge what is the most fundamental area of mathematics. I mean, this will change over time. There are areas of mathematics that didn't exist 100 years ago, which are absolutely fundamental now. Like modern algebraic geometry is very abstract. There's no counterpart until the 20th century. So I think it's premature to decide.
Check.
I would agree with what Terry just said. I think that the analog of the problem of finding a small set of principles from which you can understand everything in mathematics is largely a solved problem and has been so for 100 years or so. We have a small number of axioms from which we can build all of the mathematics that we know today, and it's searching to replace that is maybe not what most of mathematics is concerned with now.
Okay, so that brings me to the question of the fragmentation of math. So there is this famous ABC conjecture that has been described as the most important unsolved problem in Diophantine analysis. In 2012, Shinichi Mochizuki published a proof, but it runs 500 pages, written in mostly new symbolic language. And it is, at least in the popular literature, they say that 2 years later, no one really knows if this conjecture has been proved or not. So my question is, irrespective of whether that is correct or not, do you think that there will be more and more cases in the future that somebody will come up with an important proof which other people will take a long time to either confirm or disprove?
No. It happens already. There were some results in kind of graph theory, which also was able to understand, and was published by a journal, but nobody knows who's the referee. No, it's happened. Yeah, that. But
something as important as the ABC conjecture.
Yeah.
In the end, people will get to the bottom of whether it's true. It might take a couple of years.
Yeah.
And I think the example of the ABC conjecture is a bad one, because I think there are other reasons in this case. It's written in a very strange way, not in the usual way that mathematicians write things. That's put off other people reading it. And I don't think that's for any necessary, it's not for a mathematical reason, it's just the style that Shin Mochizuki chose to write in. Maybe a better example is the Perelman's proof of the Poincare conjecture. That was written in a normal mathematical way. Perelman was willing to answer questions. And it took mathematicians a couple of years, lots of people worked on it and quickly became, within a couple of years, became verified.
There are really examples of complicated proofs, and for example, algebraic geometers almost all trusted resolution of singularities, and very few really studied the proof, because it now became human accessible. But for when it started, it was really trust. I think it's people.
But some did. I mean,
it's some
just
did.
Here and now. I mean, we certainly don't all verify the proof of every theorem we use, but we trust that if a number of good people with a good track record have studied it.
And there are people who work in formal verification.
Yeah.
They take complicated theorems, let's say the Phi-Thompson theorem, and they do convert it into computer verifiable. So.
I would also say this is not a particularly new phenomenon. Like 150 years ago, the Riemann mapping theorem was stated by Riemann. An inadequate proof was provided. It was, something which is important in complex analysis, and it didn't get sorted out for more than 50 years. Also, I would say that...
But did he actually provide the proof?
He provided a proof which was inadequate. And would say that the question of whether or not something has been proved, maybe that is a question that can be answered yes or no, but even once there is a proof, in the case of a very complicated proof, really isn't the end of the story. If there's a 500-page proof of something and it's important enough that people are going to read it, they're going to process it, they're going to find simplifications, hopefully dramatic simplifications, and this is one of the ways that mathematics moves forward. And this is maybe an activity which is undervalued in the culture of mathematics, the activity of cleaning up very complicated stories and rendering them comprehensible to the rest of the mathematical world.
I should also say that often when there's a breakthrough, I mean, it may be a 100-page paper, but if it's a really important, if it's a really good piece of mathematics, often you don't have to read the whole 100 pages to realize that something really good is happening. For example, Perelman's proof-of-point Gray conjecture. Within the first 5 pages, there were these new Montanesi formulas. There's a new way of thinking about Ricci flow. There were lots of new ideas already in the first few pages that got people very excited even before they had digested the rest of the argument. That something very original was happening and something potentially very, very useful.
I think that's very important. I mean, I think to a large extent, people don't. If you have one doesn't read a mathematical paper, to a large extent. What one gets is the idea to reconstruct the argument. So it's not that people, generally speaking, would be checking a proof in the sense of checking the logic line by line. They would go and extract the fundamental idea. That's really the essential thing, I think, to point to make.
Terence, and you said that there are certain people that basically go and look at every proof, and they then design a computer model that should prove it with the help of the computer?
Not every proof. The computer verification is nowhere near at an automated stage that we can just sort of feed in, journals and formalize everything. That one day that may happen. I mean, one day we may actually write our papers not in LaTeX, but in some language which some smart software will convert to a formal language, and every so often you get a compilation error. Computer does not understand how you derive this step. So right now they're focusing only on a select few sort of test theorems of mathematical significance.
And do you think computer verification will get to that stage that basically it will be able to verify every new paper?
Oh, I hope so.
Several people working on it in several groups. Yeah.
In some areas of mathematics, I think you can do that almost already. I think others are more like anything which is very visual with diagrams, and so some parts of mathematics are hard.
But does it mean that if the computer will be able to verify, then it will also be able to come up with new ideas?
No, it's PNP problem. Yeah.
Not necessarily, but computers can certainly be useful for other things. For example, already there's this database called the Online Encyclopedia of Integer Sequences. And it's every time a mathematician discovers an interesting new sequence, they often enter it in this database. And sometimes there's a match with the previous sequence entered by somebody else. And from this database, a lot of new mathematics has been discovered, a lot of unexpected connections. So that is certainly one way in which a computer can help suggest conjectures, for instance.
Also, somebody made, but it's not in infancy stage, database of interesting real numbers. Mm-hmm. If you have something 100-digit number.
Yes.
It's not something I know anything about really, but perhaps the classification of finite simple groups would be an interesting case where to have the proof verified by a computer, because it is something which might be amenable to that, and it is an enormous proof that would be.
Enormous theorem.
Interesting test case.
10,000 pages long currently. Yeah. So one fragment of that, the Feit-Thompson theorem, is 200 pages long. That has been formalized. So that's 2% of the job done. Okay.
Well, that brings me to a specific question for you, Terence, that short of like getting computers proving everything, you designed a project that at least is trying to put a few human minds together. It's called Polymath. And can you elaborate on how important do you think the collective intelligence is in mathematics going forward?
So first of all, the Polymath projects were not invented by me, but by Timothy Gowers 4 years ago. But I did run one of the most recent ones. And I'll talk about it, in fact, after the lunch break. So this is a very interesting new paradigm for doing mathematics. So not just one or two people working in isolation, which is the conventional model, but really crowdsourcing, trying to collaborate with people who you might not think of as natural people to work on a project. I think at present this is still a very limited model. There's only certain types of mathematical problems for which you can really break it up into small pieces that different people can work on. But I think there'll be more of this in the future. I mean, the sciences already have lots of big collaborative projects. I mean, they're way ahead of us in that respect. I think you'll see a lot more, maybe not necessarily polymath, but a lot more projects where hundreds or tens of mathematicians are working.
And what was the most significant example of something being collectively solved, and how many people participated so far?
Okay, so there was the first polymath project where we had to, where we found a new combinatorial proof of a very difficult theorem, and that maybe had 24 people working for about 2 or 3 months, and we found a proof that was a lot simpler, gave much better bounds than the previous proofs that appeared in the annals. The most recent project that concluded, also about 24 people, that ran for about a year. We were improving this bound and prime gaps. Well, you'll hear about it after lunch. So there, the breakthrough had been done by an individual mathematician, Yitang Zhang, last year, but we greatly simplified his method, made it much more efficient. We now understand exactly what the limitations are of his technique. So it's not yet sort of these online massively collaborative projects are not so great for producing the initial breakthrough, but for refining an existing breakthrough and clarifying it, it actually seems to work quite well.
But as I understand that particular case, there was this polymath project that improved things, but while that was going on, an individual or 2 individuals, Maynard and maybe you, Terry, had more fundamental insights outside of this project, which actually did far better than the collaborative project.
Right. I'll talk about this is true. That while we were improving the original argument of Zhang, there was a separate breakthrough made by individuals. Okay. But then later we combined forces actually, and we incorporated this new idea into our project, and now we have a bound which is better than either of the two. So you need a mix. I mean, not every piece of research in the future will be done by individuals. Not everyone will be done by massive groups. We need both.
Can you imagine a massive group making a fundamental breakthrough?
Yeah, perhaps not with our current paradigm, but it's maybe with a different model. Yeah, it's possible. Yeah.
I think there's actually a smooth transition when some of those 12 individuals would be computers, and you will not know that they're computers. And then there will be just more of them, and that's how this thing's going to happen. So, Jacob, what do you think about it?
I'm not going to wait.
I'm talking about collaborative rather than individual.
I don't think most of the mathematics that I have been involved with, a massively collaborative effort would have been helpful. But I can easily imagine that there are examples where it could be.
And are you, Terry, involved in this project right now?
There's no currently active polymath project right now. I'm kind of exhausted after 1 year of moderating the previous one. And this is actually one bottleneck, is that there's not many people who are willing to run these things for a long period of time. But sometimes we react to events. And another thing that the polymath projects are good for is actually proof checking. This is something we mentioned earlier. There was, a few years ago, a claim proof of P equals NP, that we actually set up a polymath project to check the proof line by line. And unfortunately, it turned out to fall apart. But this is one place where a massively collaborative effort can actually be quite efficient.
Yes, so I really wanted to ask this question about computers. We already have been discussing it for a while, but you do imagine the maybe in 100 years or 1,000 years that like it happened in chess when computers took over, and humans are still playing the tournaments, but everybody knows that computers are better. So, is it conceivable for you that this will happen to mathematics?
I think computers will make we'll be able to do things much more efficiently with the right computer tools. So, for example, with search engines now, if you type in a search query into Google, say, often it'll come back, did you mean this? Right? And often you did. And one can imagine, if you have a really good computer assistant, you're working on some math problem, it'll keep suggesting, should you do this? Have you considered looking at this paper? And you could imagine this would really speed up, actually, the way we do research. Sometimes you are stuck for many months because you just don't know a key trick that is buried in some other field of expertise. But if some sort of advanced Google or something can suggest this to you. So I think computers. We will use computers, to do things much more efficiently than we can currently do. But it will still be humans, driving the show. I'm pretty sure.
Maxim, do you imagine anything like that happening?
I think it's perfectly possible, maybe in our lifetime. And
So why do you think so?
No, I don't think it's to make artificial intelligence. It's very hard and so on. I think it will be pretty soon, I suppose. Yeah.
So we will have done a problem with the prize. Yes, so I'm just thinking about it. I'm thinking about two things. One is splitting among hundreds of people, and then another one is giving to a program. But you are sort of a contrarian here in a way. You are a contrarian here, saying that it will happen so quickly. So what makes you so optimistic?
Optimistic? No, it's actually pessimistic. Okay. No, it's kind of also, I thought myself a little bit about, no, I don't think there's really fundamental difficulties, yes.
And why wouldn't you just work on that? Because this is
No, I think I think it will be immoral to work on it,
I'm no expert on it, but isn't the way the computer played chess not really very intelligent? It's a huge combinatorial check, and inventing the sort of mathematics you've invented, that's not combinatorial checking, it's entirely conceptual.
Yeah,
is there any case we know of computers doing anything like that?
We don't know examples, but I don't see it's not inconceivable.
It's not inconceivable, but But I would be very surprised if we saw a computer win a Fields Medal in our lifetime. Or the Breakthrough Prize.
Well, one could imagine that a computer could discover just by brute force a connection between two fields of mathematics that wasn't suspected.
That's more likely, yes.
And then the person on the computer would actually be able to flesh it out. Maybe he'll collect the medal. Okay.
The problem Fields Medal is this 40-year-old threshold. So how would you sort of? So Jacob, are you sort of terrified a little bit with what Maxim is saying, or you are kind of cool about that?
I think I'm not too worried. 1,000 years, hard to imagine what any of us are going to be doing.
Or us, probably not.
No, actually, Kolmogorov thought that mathematics will be extinct in 100 years. He had estimate, because he really calculated kind of number of neurons, collections, and you cannot make the head more than something like one cubic meter and so on. Because so he was his kind of maybe crazy estimates, but he was also thinking about natural boundaries.
Well, on that note, I wanted to maybe open this for some questions. They can be philosophical or more specific, but I think we're ending on a high note here. So, any questions?
Yeah, I would like to ask the panelists, what if they could
suggest some improvements to computer math software or computer-aided computational tools of any kind that could really have the greatest potential for moving forward research mathematics in the sense of humans working with computers and computers discovering and fleshing out details, what would be the most useful development here?
One thing I would wish for, I don't know if I think it's not still within current capability, is really smart semantic search for a mathematical concept. Like if you have, like, if you have some cute lemma, for example, that you just proved, and you want to know, is there something like this in the literature? You can try typing in what you just did into Google, and this usually does not, unless it's you have exactly the right keywords, you usually don't get something very accurate. But if you had a very smart search engine that could detect when two mathematical statements were similar, then having that drawn to your attention would be quite useful, I think.
If we're talking about computer-assisted proofs, then it seems to me that the main obstacle is user-friendliness. If you want this to become part of the culture of mathematics, that when you submit a paper, you also have to submit a computer verification that what you proved in the paper is correct, I think it's very unlikely that this will become part of the culture of mathematics. But if you wanted to, then what you need is computer assistance that mathematicians are actually willing to use so that it doesn't take 100 times as long to provide that certificate as it does to write a mathematics paper the usual way.
What we're talking about, it's not exactly this question, but we're talking about computers in mathematics. I think we really should say they have already had an enormous effect. I mean, mostly as experimental tools. So the discovery of the Birch-Swinnerton-Dyer conjecture by Brown-Birch and Peter Swinnerton-Dyer in I think the 1950s, with very early computers. They did, while knowing a lot of number theory, they did an enormous amount of computation and came up with this conjecture nobody expected to be true, and it completely changed the direction in which number theorists were working for now 60 years or something. Andrew Odlyzko computed the zeros of the Riemann zeta function and saw patterns that connected it with random matrix theory. Again, had an enormous effect on analytic number theory. So computers as an experimental tool have already had an enormous impact as a theorem-proving tool. So far it hasn't, and we disagree about the likelihood that it will, but they certainly are of crucial importance in mathematics.
Tim Gowers right now is working with, I think, an artificial intelligence person to actually create a smart theorem prover that doesn't use brute force, but really sort of uses human-style problem-solving techniques. So apparently they can get to the level now of a bad undergraduate topology student. So you have some very restricted language, like say metric spaces. You want to prove, let's say, the union of two open sets is open or something, and they can actually find a proof, but not by brute force, but by trying sort of standard moves.
But that's when a human has already created the field of topology and the key notions, and then it becomes a sort of symbol-playing game almost.
Right. So that's where they're at right now. But yeah, but there's some work in this direction. Oh.
Could you comment on the making of a mathematician? Would you say it's motivation, training, mentorship, luck, wiring, genetics? What is it that distinguishes the mathematicians up there?
All those things.
It's very diverse, actually. I mean, so the stereotype is someone who has mathematical talent at a very early age, and I guess so I myself was accelerated as a child, for instance, but certainly not everyone is like that in mathematics, and not necessarily the best people in mathematics are not necessarily the ones who showed early signs of mathematical ability. Some came in the field quite late and made really important contributions.
Let me try to answer for Maxim. It doesn't matter because it's a simulation. Okay, what is your...
No, I think actually everybody can do mathematics. You just have to learn. And I mean, I just thought like 5% of populations are dyslexics, and I said, do I know dyslexic mathematicians? And I think I know, yeah, some really great mathematicians who even show formula. You can, and here the conversation stops. Yeah, yeah, so it's quite possible.
Sometimes it's an advantage. Like if you can't you can't visualize things in a certain way, you develop other mental faculties to.
As Terry said, mathematicians are an extremely diverse group of people. I mean, somebody like Thurston apparently just saw things geometrically in his head. Other people, almost entirely symbol manipulation. Some people are combinatorially quick and fast, which is extremely helpful. Other people try and think conceptually or uniquely.
So, Simon, what do you think? Is this a formula?
There are several different ways of thinking about mathematics, and some people can do both, but both very well. But a lot of people primarily do. I primarily think visually, not kind of combinatorially or symbolically, but other people are quite different. Yeah.
And if I will ask each one of you, can you name 3 greatest mathematicians of all time? Of course, the first one has an advantage. So, if
Well, I don't know.
let's say not living today. Simplify.
I mean, there are standard answers: Gauss, Euler, Hilbert, maybe. Now it's getting harder.
So, Terry, what is it?
It's the same. We in our coffee room, common room at UCLA, we have this standard tableau. I think it's 5 mathematicians. I think it's Fermat, Euler, Newton, Gauss, Hilbert, and then it stops. Actually,
including Newton.
Yeah.
You said Newton?
Riemann, yeah. Okay, you have the same 5 pictures. Yeah. Well, it gets difficult after a while because by Hilbert's time, actually, mathematics had expanded to the point where it was no longer possible for one mathematician to really cover all mathematics. Hilbert was maybe the last, maybe von Neumann. But yes, and then after that, I think it's really personal taste. I mean, yeah.
So, Jacob, what are your favorite 3?
I don't want to touch it.
Yeah, 3 I think were already named. Yeah, so it's
Because the more
no, but you're alive. Yeah, no, you ask.
Yes, I guess he's alive, but but retired. Sorry.
Yeah.
Simon, you agree with the all?
I would vote for Riemann myself. One striking thing about Riemann is that his collected works are about 100 pages, but his influence has been sort of unparalleled, I would say. So
and what are the other 2?
I'm sorry?
And the other 2? 2 more?
Oh, 2 more. Well, in my own kind of Poincaré, in my own area is the
Father-son team in mathematical history. I think the answer is Gauss and his father.
Maybe a question more to Maxim. Maxim mentioned that quantum theory was example when mathematics go first and precede discovery of real, like new nature of quantum nature of world. And would you imagine that something similar may happen based on the contemporary mathematics, like algebraic geometry, exact solutions? Because this is fascinating connection between algebraic geometry and exact solutions of physical equations described.
20 years expected to go from string theory, Calabi-Yau. Okay, yeah. That's exactly what they expected, yeah. But
no, I think beyond string theory, because there are exact solutions which relates to algebraic geometry, to like theta function and exact solutions which you can touch just by geometry, some imaginary by imagination, and then get maybe you can think to predict something, new discoveries in the future, which will open more deeper understanding of nature, like quantum theory. It was really singular event.
Yeah, no, I would be surprised, in fact. Yeah. No, I would be surprised. Yeah, I would be surprised. I think nature should be the center of the non-mathematical. Yeah, so it's kind of it's too much of mathematics. Yeah.
Yes. Thank you.
The modern stage.
Thank you.
Yeah.
There was a brief mention of foundations in the earlier discussion. I was wondering if anyone would be willing to comment about their thoughts, opinions about the prospects for the Univail Foundations program, and whether that is a contender for changing these things. And
no comment.
The person you need to ask is not sitting here. But, yeah.
And maybe as a follow-up to the discussion about computer-verified proofs, is anyone willing to bet against the short time scale, like 25 years, for that being widespread use in mathematics?
Oh, I'll take that.
Yes, me too.
Yeah, okay. Widespread in some fields, maybe, at least. Yeah.
Maybe one last question.
So my question to all the panelists is, you are all celebrated mathematicians. What's your best advice for us aspiring young mathematicians?
Pick something you're interested in and give it a lot of thought.
Yeah, exactly.
Ask yourself really dumb questions. Like, don't just take a fact of mathematics as received knowledge. Just always question it and see if you can do better.
Can you make an example of you asking dumb questions and doing well?
Well, I mean, this happens long before you actually work on a research problem. It's when you're learning the subject, like, you know, you learn a certain lemma is true for all, I don't know, say, sigma finite algebras or something. What is not sigma finite? You know, why do you have to prove things this way? Can you prove things using some other tool? And you'd always keep tinkering, right, with the mathematics you have.
Maxim, what's your advice?
Yeah, just to learn really different areas of mathematics. It's very important. Then you see analogy and
go to talks.
Yeah.
Within limits. I mean, you can go wrong by trying to learn too many areas of mathematics and understanding none of them. At least in my own life, I try to do one.
Simon, what's your advice?
Make sure you're doing what you like doing. I mean, there's nothing worse than... So you've got to really want to have a passion for what you're doing. I think that's...
Well, I want to thank everybody for bearing with us, and thank you for coming here, and once again, congratulations with the prize. Thank you.